Hello everyone, this is Ayman Neg. In this video, I'm going to show you how we can use TinkerCad software to apply Thevenin's theorem. So the circuit shown here, I will first do the theoretical calculations to find the voltage V node across the 6K resistor, and then we're going to show how we can apply this in the lab. Okay. So first, let's try to solve for V node using Thevenin's theorem. So the Thevenin's theorem states that this circuit is equivalent to an independent voltage source. We call it V Thevenin, connected in series with a resistance R Thevenin, and we uh, exclude the load resistance from this circuit. So we are not going to use the 6K resistor in getting R Thevenin and V Thevenin. So we remove RL, the load resistance, from our calculations. And after we get R Thevenin and V Thevenin, we return back the 6K resistor to find the value of V naught. So let's see the steps we need to apply to find V Thevenin and R Thevenin. So theoretically, V Thevenin is the open circuit voltage across the load resistance, which is in our case the 6K resistor. And by open circuit, we mean we will remove RL. So the circuit now to find V Thevenin will be the circuit without the 6K resistor. Now, after we removed RL, then we call this voltage V Thevenin. So here we have a single loop. Of course, we don't have any currents flowing in the 6-volt battery because it's the terminal is open, so there is no current flowing in the 6 volts battery, but still it will affect the value of V Thevenin. But at least we know that for this circuit, the current will only flow in this loop. Okay, so it will flow in the 3-volt battery and in the two 2K resistors in the 4K resistor. It will not flow in the 6-volt battery. So since we have a single loop, we can easily find the current using Ohm's law. So I is equal to the 3 volts over the total resistance in the loop, which is 2K plus 2K plus 4K. So this is equal to 3 over 8 milliamps. Now, this current is flowing in the counterclockwise direction. Now, to find the voltage V Thevenin, we will take a path from the positive terminal to the negative terminal of V Thevenin. So we will go this way, then this way, then we end at the negative terminal. So we have three components. We have in this path, we have the 6 volts battery, we have the 3 volts battery, and we have the 2K resistor. So we have three drops. So the value of V Thevenin will be the result of the three drops, which is the 6 volts and the 3 volts, and also the drop across the 2K. Since the actual current is flowing against the path we took from the positive to the negative terminals, then the drop will be with a negative sign, which is minus 2K times the current, which is 3 over 8 milliamps. So the voltage will be equal to 9 minus 6 over 8, which will be equal to 8.25 volts. So this is V Thevenin. The first step we have already got this source. Now the next step to get is to get our Thevenin. So our Thevenin is the resistance seen by the load when all the independent sources are switched off. So in the original circuit, here we have two independent sources, the 3 volts battery and the 6 volts battery. So we will turn off both of them, and we do this by short circuit. So if you want to turn off a voltage source, we short circuit the battery. If we want to turn off a current source, we open circuit the current source. So in our case here, we have only voltage sources, so we will turn them off by short circuiting both sources. So the circuit will look like this. And we are still calculating the resistance at the same two terminals at which we calculated Thevenin. So this is a 2K, and this is 4K, and this is 2K. And as you can see in both calculations for Thevenin and Thevenin, we did not include the 6K resistor in our calculations. Now we can imagine a source connected to these two terminals. Now we want to see how much resistance is seen by this source. Okay, so you can see that we have a 2K resistor in one terminal, in one branch, and in the other branch, we have the series connection of 2K and 4K. So we have this branch 2K parallel to 6K. So this is the total resistance seen um, by the terminal from the terminals of the load. So R Thevenin is equal to 2K parallel to 6K, which is 2 times 6 over 8. This will be 1.5K. Okay, so we got our Thevenin, we got Thevenin. Now we can use these values in the equivalent circuit. So the equivalent circuit will have 8.25 volts as the voltage source, and our Thevenin, as we mentioned, is 1.5K. After this, we connect back the load resistance, which is the 6K resistor. And now we need to find the output voltage V naught across the 6K. So this circuit is very simple to analyze. V naught will be simply a voltage divider from the 8.25 source. So V naught is equal to 8.25 times 6 over 6 plus 1.5. The value of this voltage is 5 over 3 volts. Okay, so this is how we can use Thevenin's equivalent circuit to find any variable, whether it's current or voltage, across a certain component in the circuit. In our case here, we are finding equivalent circuit around the 6K resistor. We exclude the 6K from the calculations, get V7 and R Thevenin, and finally we connect back the load resistance to find the voltage across the 6K. Now I'm going to show you how you can apply these steps using the lab components. So for this purpose, we are going to use TinkerCad software. Now we will see how we can connect this circuit in the lab and apply um, uh, the Thevenin's or verify Thevenin's theorem in the lab. So I will add a breadboard here, and I'm going to connect exactly the same circuit that we analyzed in the. So here we have the series connection of 4K and 2K. So for this, I'm going to use resistors. Now we have the series connection between two resistors. Next we have another 2K resistor connected with a battery. So here's another resistor, and we will see the voltage source. We can use a power supply for this purpose. So let's look for the power. So the terminal of this 2K resistor will be connected to the ground. We assume that this would be the ground node. So here we connect this to the ground rail, and the battery will be connected between the ground and the other 2K resistor. Okay, now we finished the connection of the 3 resistor battery. We now have the 6-volt source, so we will use another power supply for this purpose. Um, we connect the plus, we have the minus to the same or the common node between the resistors. And the positive terminal is open circuit. As we mentioned, it's not connected to the load resistance yet. So I will not use the 6K resistor. I will connect the circuit without the 6K resistor. And this is what you should do actually in the lab to measure Thevenin and Thevenin. You should disconnect the load resistance from the connections. I can use some multimeters to verify the values of the batteries. So let's put a multimeter. So I will use one of them to measure the voltage across the battery. And the other multimeter to measure the voltage across the other battery. Finally, we need to measure Thevenin and Thevenin. So Thevenin, as we mentioned, is measured between these two nodes. So I will connect a multimeter between these two nodes. So let's use this another multimeter for this. So the positive terminal will be connected to the positive terminal of the battery, which is this connection, and the negative terminal of the multimeter will be connected to the ground. Okay, now let's set the battery voltage. So for this battery it's 3 volts. So here for this power supply, I will just set the voltage to 3 volts. For this battery, I will set it to 6 volts. The resistance we have 242, so this is 2K. And this is 4K. And this is 2K. Okay, now let's run the simulator. We see here we verified the values of the batteries. So one multimeter is measuring 6 volts, the other is measuring 3 volts. And we see here that the multimeter connected at the terminals of the load is 8.25. We verified the first result, that Thevenin is equal to 8.25. Okay, so in the lab you are not required to do the theoretical calculations, but this will be very useful for you to verify the experimental measurements. Okay, so before going to the lab, you should, if you have the circuit diagram, you should do the theoretical calculations first before doing the measurements in the lab. Now let's see how we can measure our Thevenin in the lab. So what we are going to do is I'm going to turn off the batteries. Of course, in TinkerCad, you can do this by just setting the batteries to 0. Okay. In this case, the two power supplies are turned off, and now we need to measure the resistance. So the multimeter, I will set it to measure the resistance instead of the voltage, and then I run the simulator again. You will see here that the measurements is 1.5 kilo ohms, which is the same as the result we got here. So we verified the theoretical calculations, and we showed how we can measure the R Thevenin. Now it will be difficult for you to just set the voltages to 0 in the lab. So what you will do instead is you're going to short circuit. Okay, so as you mentioned, you short circuit the voltage source to remove its effect from the circuit. So that's what I'm going to do, so that you know that the actual procedure you're going to do in the lab. So if you are short circuiting this source, the 3 volts, this means that the 2K resistor will be connected to the ground. And you can do this by just putting one wire between the 2K and the ground. So now we have short circuited the 2K resistor, or sorry, we have short circuited the burst voltage source. To short circuit the 6-volt source, let's remove this, or let's just remove the wires. And what we need to do is we need to connect the measurement terminal to the 2K resistor. So we are measuring the voltage here. We connect this point to the common point. Now, if you run the simulator, yeah, there was a gap here. That's why it was not measuring the correct resistance. Let's see now. Yeah. So now, as you can see, the first multimeter is measuring 0 volts. This means that we have a short circuit. I think this wire should be here. Let's stop the simulator. This point should be on the same line as the other two nodes. Let's remove the wire and connect it back like this. And let's see. Yeah, so now we verified that we have short-circuited the both voltage sources, and the measured resistance was 1.5K. Okay, so this is how we're going to measure R Thevenin and V Thevenin in the lab, given a circuit with independent sources. Now let's verify the actual voltage across the 6K. So to do this, I will just connect back the supplies. So let's remove the short circuits. The plus to this terminal, the minus here to the ground. The plus of the other source is at this point, and the negative at the common node of the resistors. Now what we're going to do is to connect the 6K resistor, okay, the load resistance. So let's connect it between the two terminals. So now we have the resistance between the this node, which is this node, and the ground, and let's set the value to 6K. Now let's run the simulator. We're still switching off the supplies. Let's put the supplies back, 3 volts and 6 volts here. Let's set this to voltage. This should actually be 1.5. Value should be 6.6. Okay, so as you can see, we verified that um, the actual calculations um, or the theoretical calculations had a mistake by comparing the experimental results with the theoretical results. So we got the values of V7 and R7 correctly. I just like made a mistake in applying the voltage division, and as you can see, we got 6.6, which is the same value we got from the simulator. Here, 6.6, the value of the voltage across the load resistor or the 6K resistor. Okay, so that's what you are going to do in the lab. You're going to connect your circuit, measure V7 and R7. We just wanted to verify the theorem, and it's very helpful, as we mentioned, if you want to replace the whole circuit with a single source and single resistor. Of course, like using the equivalent circuit will simplify the connections. For example, you can replace the whole circuit that you measured the V7 and R7 and 4. You can just use one battery and one resistor. So in this example, we use two sources and three resistors. You can replace 5 components with only 2 components, with a single battery and a single resistor. Okay, so I hope in this video that you have an idea about how to do the Thevenin calculations and theoretically, and how to apply them in the lab. Thank you.